Welcome to the Explainer. Today, we're diving into something pretty incredible: how modern factories are built, tested, and pretty much perfected, all inside a computer, long before anyone lays a single brick. I mean, think about that question for a second. How do you test drive a factory? It's not like you can take a billion-dollar production line for a spin, right? Well, maybe you can. This is the exact problem manufacturing simulation was born to solve. The idea is to create a digital twin, a virtual copy you can push to its limits, find all the hidden flaws, and kick the tires, so to speak, before it costs you millions in the real world. So let's see how it's done. All right, first things first. To really get why the solution is so brilliant, you have to appreciate the problem. A modern factory isn't just a building with a bunch of machines. Oh no, it's more like a giant, incredibly complex puzzle where one piece out of place can bring the whole thing to a screeching halt. And these aren't just little separate headaches. They're all connected, kind of like a line of dominoes just waiting for a push. A single machine failure, bam, that can easily topple into a delivery delay. That buffer, the waiting area for parts, if it's sized wrong, it creates a massive bottleneck that knocks over the next process and the next. It's a chain reaction, and sometimes fixing one problem just creates a new one somewhere else. So, faced with this tangled web of issues, what's an engineer to do? Well, they open up a powerful digital toolbox. We're not talking about wrenches and screwdrivers here, but a whole suite of sophisticated software built specifically to design and analyze a factory in the virtual world. And at its heart, this is really what it's all about. You're building a perfect digital replica. Think of it like a sandbox where you get to play. You can break things on purpose, you can flood the system with a million orders, or try out a totally radical new layout. And there are zero real-world consequences. It is, without a doubt, the ultimate what-if machine for anyone in manufacturing. Now, when we look inside this toolbox, we find a few different trays of tools, each designed for a very specific job. You've got your process timers, which are all about flow and sequence. Then you have your smart agents for modeling independent decisions. And of course, you've got the heavy-duty power tools for looking at the entire system all at once. Okay, let's grab the first tool. These are the process timers. They're probably the most fundamental and widely used tools in the entire kit, and they are laser-focused on sequence, timing, and flow. The fancy term for this is Discrete Event Simulation, or DES. The best way to think about it is to imagine you're tracking a single package moving through a giant warehouse. DES models its journey as a series of distinct steps, or events. Arrives at the dock, gets scanned, moves to a conveyor, gets sorted, loaded onto a truck. It's all about what happens at each of those points, and crucially, the time between them. And this is where the rubber really meets the road. Engineers use DES to answer really practical questions, like what's the absolute perfect size for those buffers we talked about? Or what happens if we try a completely different factory layout? Will this new control system actually work? It's all about optimizing the flow. So if you want a simple way to remember it, just think of DES as the precision stopwatch for the entire factory floor. Its whole job is to answer the critical questions of when a part will get somewhere and where things are getting clogged up. It is the key to mastering the logistics of the line. What happens when the things moving through your factory aren't just passive little parts? What if they can make their own decisions? Well, for that, we need to pull a totally different tool out of the box: the smart agents. This brings us to agent-based modeling, or ABM. Now, this approach kind of flips the script. Instead of modeling the process from the top down, you build the system from the bottom up. You create these little digital agents. Maybe it's a worker who has to decide which task to do next, or a self-driving forklift that has to navigate obstacles. You give each agent a set of rules, set them loose, and then watch what happens. Here's probably the best way to think about the difference. The first tool, DES, is like having a perfect blueprint of a highway system. It tells you exactly where the roads are and what the speed limits are. Agent-based modeling, on the other hand, is like simulating the behavior of every single driver on that highway to see if a traffic jam just sort of emerges on its own. One is about the system's design, the other is all about the unpredictable behaviors within that system. All right, but sometimes you need to either zoom way, way out, or you need to model something incredibly specific and complex. And that is when engineers break out the really specialized power tools from the toolbox. And we're talking about some seriously impressive tech here. You've got things like system dynamics, which lets you see the giant ripple effects from one tiny change, like how a small inventory decision today could create a massive problem 6 months down the road. You have other tools that are designed to model pure randomness and chaos, because let's face it, the real world isn't neat and tidy. And now, of course, you've got AI and deep learning being used to create incredibly realistic simulations, and even hybrid models that mix and match the best of both worlds into one super tool. So we've looked at all these tools, the timers, the agents, the big power tools. Let's zoom back out. What's the big picture here? What's the ultimate goal of all this digital wizardry? It really all comes down to this single, powerful idea: the power to try again, the power to build, test, and perfect a factory not once, but countless times. It's the ability to fail fast and fail cheap inside a computer, so that when you finally build it in the real world, it's as close to perfect as you can possibly get. And this is exactly why it matters so much. The end game here is a whole new generation of factories. Factories that are cheaper to get up and running, way more efficient to operate, and, this is the big one, far more resilient. They become systems that can actually adapt when something goes wrong because they were already tested against those very scenarios in the digital world first. And that kind of leaves you with one final, pretty mind-bending thought. We've seen how this is completely changing the factory floor, but what if you could apply this toolbox to anything? The traffic flow of an entire city, a global supply chain, maybe even a whole economy. What kinds of massive problems could be solved if we could build, test, and perfect our world in a computer first? Thanks for joining us on The Explainer.